Hi, everyone. My name is Lucas Janson. I'm an assistant professor in the Department of Statistics at Harvard, and I'm very excited to talk to you today about Floodgate, which is a new method for getting inference for model-free variable importance. So let's start with my co-author, who is my amazing PhD student, Lu Zhang, and she's a rising fourth-year PhD student. She deserves really the lion's share of the credit for this. She's been really amazing. So, look out for her because she's going to do great things. So, so let me start with the setup. So we're in a regression setup, which means we have an outcome of interest, which I'm going to call y, and then we have a whole bunch of explanatory variables, which I'll call x and z, but in particular x will be the particular variable that at any given moment I'm actually trying to infer its variable importance. And by variable importance, I of course mean its importance in explaining y or predicting y. And so I have these x and z's, and x is going to be the one I focus on. Z's are going to be the rest. So I have a p+1 dimensional covariate space, and the z's I'll just sort of call the confounders or the nuisance variables. And I may care about all of my covariates, in which case I'll just sort of rotate which one is x, and I'll just call the other one z's. But for simplicity, since we're going to focus on one variable at a time, I'm just going to say the one I'm focused on is x, and all the rest of them are z. And hopefully I don't have to justify too much what kinds of applications or regression setup or caring about variable importance might be for, but just to be concrete, we can think about y, for instance, as a disease or a trait, and the covariates as single nucleotide polymorphisms or SNPs or gene expressions, and we might want to understand how big an impact those genetic covariates have on y. We could have y being, say, the approval rating of a politician, and the covariates being some sort of characteristics or policies that that politician has, and we want to understand, how do people, what factors affect someone's approval rating of a politician or how they view a politician. And another example, y could be a medical outcome, and the covariates could be some sort of entries in the patient's medical history. And again, we want to understand that relationship better. So, these might be high dimensional, they might be low dimensional, they might be really any kind of regression setup. I just want to sort of generically say I want to understand how big x's effect is on y. All right, so I think when we talk about variable importance, I think the first question we often ask, and it's one I've worked on, it's what a lot of people have worked on, is the variable important? So is x important or not? And this is sort of the binary question. And that's a super important question, especially when you have tons and tons of variables, and you need to at least narrow your search down to focus on a few. But I think the sort of immediate next question, I claim sort of question 1 star, is how important is the variable? And there has been work on this as well. I think it isn't paid as much attention as the first question. And in particular, I think when we want to answer this question in a particular way, we're going to see that there really hasn't been much work done on it at all. And so there's going to be something novel for us to add. So in particular, the goal at high level I want to think about is that if I'm in some sort of complex regression setup where y depends on the covariates in a complicated way that I don't really understand, I want to know more about. What I really want is some sort of interpretable but sensitive measure of variable importance. And of course, I want to be able to do inference for it, and I want that inference to be valid, and I want my inference, say, a confidence interval, to be as narrow as possible. So to dig into these 4 underlying words a little bit more, by interpretable, I mean that my measure of variable importance should be a function of the data generating distribution. It should be, non-random. It should be fairly simple, and hopefully a human looking at it should sort of understand what it means. But at the same time, it should be, not so simple that it can't detect the kinds of interesting dependence that we may care about. And in particular, we don't want this thing necessarily to just pick up on sort of main effects or linear effects. We would like it ideally to be sensitive to nonlinearities and interactions of all kinds of orders that we may care about in the relationship between x and y. Those may be important relationships, and we want to be able to be sensitive to those. And then the inference should, of course, be valid. And by valid, I just mean you have guaranteed coverage under some reasonable conditions, and we'd like it to be as narrow as possible. And of course, there's going to be some trade-off between the assumptions we have to make for validity and the assumptions we need to make to get narrow confidence regions. But under as few assumptions as possible, we'd like to get as tight confidence bounds as possible. All right, so there has been some work sort of thinking about variable importance measures before, and certainly the main example of this would be if you want to put a parametric model on the conditional distribution of y given x and z, then your measure of variable importance usually pops right out. It's just one of the parameters or some simple function of those parameters. Generally, it's quite interpretable because the parametric model usually is fairly interpretable. The challenge is that it's not going to be interpretable if that parametric model is wrong, right? So you have to really believe your parametric model, because as soon as the parametric model stops being true, it's not really clear what your estimand even becomes, right? Your measure of variable importance is no longer really well defined. Furthermore, often the parametric models we write down are fairly simplistic, and so there is a concern that they might not be sensitive either, because the model doesn't have the sort of flexibility to capture all the relationships we might think exist between y and the covariance. All right, so moving from parametric estimands, one way to make them more interpretable is to say, well, even if my model is wrong, my parametric model is wrong, I can still think about the parameter in the projected model, where I can have any distribution for y given x and project it onto the nearest version of the parametric model that I care about. And then I can look at the parameters in that model, and those should have sort of a similar interpretation. That's great, but they're going to still suffer, I think, from this sensitivity issue, where if you're projecting onto a relatively simple parametric model, you're generally not going to be sensitive to anything that's not captured by that model. And unfortunately, I think we generally only have tools for projecting onto generalized linear models, which are going to basically discard any kinds of interactions or nonlinearities that might exist in the data. All right. Now, the other thing about the projections is that they do suffer a little in interpretability in terms of because you are not actually looking at the true model parameter in the actual model, you're looking at a projection. Some funky things can happen where a variable that's completely null, it has absolutely no dependence on y after controlling for x, so it's conditionally independent of y, can actually have a non-zero value in its projected model. And vice versa. Certainly, it can miss variables that are non-null. So that's a bit of a concern in interpretability. I think the next step after that is to consider semi-parametric models. So here we think of our measure of variable importance as being the expected covariance between y and x conditioned on z. And now this is a much more flexible measure of variable importance, and it allows for sort of arbitrary relationship between z and y and z and x. However, it still only allows it's only going to capture a fairly simple relationship between y and x. And indeed, this basically represents looking through a partially linear model at the data that we have. And a partially linear model is still only going to capture linear relationships between x and y after controlling for z. So it's not going to catch any nonlinearities in x's relationship with y, nor is it going to capture any interactions between x and z and how they impact y. All right, so one of the ways that people have dealt with this sensitivity issue is to sort of think about a whole different type of measures of variable importance, where instead of having them even inspired by a parametric model, have them be inspired by very flexible non-parametric regression estimators. And the way this is done is often by data splitting. In the first half, you fit some sort of machine learning function, which can be very flexible. And then in the second half, you do inference for a measure of variable importance that actually depends on the fitted model from the first half. And this is interesting. It's much more sensitive in principle. At least it can capture sort of any kind of relationships between y and x that you might like to find. However, it suffers, I think, a bit in interpretability because your estimand itself is actually random because it depended on a regression function that you fitted to the first half of the data. And I think that can be a problem in particular for replicability. You know, if two people analyze two different data sets using the exact same procedure, they're actually going to be providing inference for two different measures of variable importance, two different numbers, two different estimates, because they're going to have fitted different regression estimators on their two different sample splits. So I think there's some downside in terms of interpretability there. And lastly, the measure of variable importance that we're going to propose in a moment, which we claim satisfies the interpretability and sensitivity properties, has been studied before, in particular in the sensitivity analysis of computational models literature, but they don't really think about inference as much there. So we haven't seen, say, confidence intervals provided for this before. And then one exception is in this paper, Williamson et al. They did consider the exact measure of variable importance that we consider, and they did think about inference, and they have a really interesting method inspired by semi-parametric inference. However, their method actually doesn't hold under the null. So actually, if your measure of variable importance is 0, if you have a null variable, which I think we expect, especially in high-dimensional cases, to be most of the variables, actually their inference guarantees don't hold. And so I think in practice, this would be hard to use. All right, so that's related work. What's our work going to be? So just to give a preview of our results, what we're going to do is we're going to present a measure of variable importance, which we call the MMSE gap, or the minimum mean squared error gap. And it's going to have a direct, predictive, causal, and explanatory interpretation. So we're going to see from the expression that it's actually pretty easy to interpret this thing. But at the same time, it's actually going to be strictly positive anytime the conditional mean of y given x and z has any dependence on x. So it's only going to be 0 if the expectation of y given x and z has absolutely no dependence on z. So it's quite sensitive, and in particular, it can pick up on arbitrary nonlinearities and interactions between x and z in their relationship with y. And importantly, it's a completely non-random function of the data generating distribution, and only the data generating distribution. And so, you know, from a replicability standpoint, it'll mean the same thing from study to study. And once we have our estimand, the thing we care about, we're going to propose a method for inference for it, which I call Floodgate. It's going to provide asymptotically valid inference. And it's actually going to be flexible enough, it's actually going to serve as a wrapper. And it's going to be a method that can take in any regression estimator. It could come from machine learning, it could come from some specific domain knowledge or mechanistic model, but any estimator you want, Floodgate serves as a wrapper around it and can take advantage of the estimation error in that regression estimator to get as small width of confidence bounds as possible. And we're actually going to prove a relationship that, you know, the better you can estimate the conditional mean of y given x and z, the narrower your confidence intervals are. But we're not going to assume you can do that in a good way, and that's important. We really only assume, say, moment assumptions on y given x and z. We're not going to assume any kind of smoothness or sparsity that would enable learning the regression function at any geometric rate. So we're going to allow you to do well if you can, but we're not actually going to assume that you can do well in terms of estimating the conditional distribution of y. What we are going to assume is that we're going to take this model X approach where we assume that x given z is known. Now, this is, you know, not necessarily a small assumption. We think it might be more reasonable, at least, than assuming something about y given x and z in some cases where, say, you have a lot of unlabeled data or a lot of domain knowledge about the covariates, but not necessarily about the outcome variable. Furthermore, we're going to quantify the robustness to misspecification in this model, and we're also going to extend our method to a version that can actually allow x given z to only be known up to a parametric model. We're going to see how to do that. So that's a preview of our results. So let's dive right in. The minimum mean squared error gap, or MMSE gap, is defined, I think, sort of as plainly as one can imagine. It's the difference of two terms. The first is the minimum mean squared error of estimating y just using z. And the second term is the minimum mean squared error, or achievable mean squared error, of estimating y given both x and z. And so by taking this difference, we're really looking at the gap in the minimum mean squared error if you use z or if you use x and z. So how much does x add to being able to predict y? So sort of from an oracle standpoint, if you could do the best possible prediction you could, how much would x add. In particular, one of the reasons we like this is that at 0, if and only if, the regression function with x and the regression function without x are exactly the same almost surely. And so it's very sensitive to any kinds of nonlinearities, interactions, anything that impacts the conditional mean of y is going to be picked up by this if x has an influence on it. On the other side, if x is a null variable, so if x is conditionally independent of y, then we're going to get a 0 value for the minimum mean squared error gap. So I think that's good. Let's talk more about its interpretability, though. So the predictive interpretation that I promised you, I think, is immediate from the definition. If we think about, the optimal predictions we could make with z, and the optimal predictions we could make with x and z, it's exactly the difference between those in terms of the mean squared error. It actually has a causal interpretation too. And so if I think about basically having, one subject who has covariates z and assigning them 2 different treatments based on those covariates, I call those x prime and x double prime. So I independently, I have some treatment assignment mechanism based on z, and I assign their treatment twice independently. I can basically then, I think of observing their 2 potential outcomes, and those will be the y's in this expectation. And the difference between those, their squared difference in expectation over z and the 2 x's, is exactly going to be the causal interpretation of the MMSE gap. And so you can sort of see this if I took out the squared inside the expectation and replaced x prime and x double prime with sort of fixed values, then this would look a lot like an average treatment effect. But this is sort of saying, okay, an average heterogeneous treatment effect, because by squaring it, nothing's going to cancel out. And that's why this is going to be a much more sensitive measure of variable importance than an average treatment effect, where positive effects in one region of z and negative effects in another region of z can cancel out. Lastly, we can interpret I squared in terms of variance explained. So how much variance is explained by x and z together, minus how much variance is explained by z alone. So it's just this simple. And I'm not sure this helps with interpretation, but I squared happens to admit a fairly compact form, which I think is nice, just the expected conditional variance of the regression function y given x and z. All right, so the minimum mean squared error gap, this is our measure of variable importance that we're going to care about. It's sensitive, it's interpretable. How are we actually going to do inference for it? Unfortunately, it's not too easy to do. And to explain why, let's define this true regression function mu star. So that's the conditional mean of y given x equals little x and z equals little z. Then we can write the minimum mean squared error gap as the expected variance of mu star. And if we just look at this right-hand expression, we can see it just in terms of mu star, its conditional expectation, and an outer expectation outside the square. Now, the problem here is that we don't know mu star. We also don't know its conditional expectation. And they're both appearing in a nonlinear function inside an expectation. And that makes it hard to even sort of get an unbiased estimate of this thing. Because if we try and estimate mu star with some mu, we're going to have some error. But that error, because there's a squaring around the mu star and its conditional expectation, those errors are going to compound. They'll never cancel out. And so it's unclear how we would even get an unbiased estimator, which is often how we start with inference problems. So one solution, of course, is that if we sort of assume that we have a really good estimator of mu star, so that, yeah, mu star is unknown, but it's sort of almost known. Well, that would put us in a much better position. Unfortunately, we then, in order to actually use this thing, we would have to, actually know that our estimator has some, nice properties. And in particular, the quality of our inference is really going to depend on exactly how well behaved that estimator is. And good understandings of the quality of estimation are sort of hard to come by. And in particular, they we don't have good theory for exactly how well various modern machine learning algorithms perform. in different types of data generating distributions. And this would certainly preclude people using estimators of mu star that incorporate some sort of fuzzy domain knowledge that's hard to quantify and certainly would be hard to prove any kind of theorem about. And so I don't want to take this route. However, if I want to take advantage still of these types of domain knowledge or machine learning algorithms to get narrower confidence intervals, I'm going to need some way to relate some estimate mu of mu star to my minimum mean squared error gap. And that brings us to the key idea in this paper, in this project. And so for starters, let's think about a lower confidence bound, right? So a confidence interval is a lower confidence bound and an upper confidence bound. I'm going to start with the lower confidence bound. What I'd like to be able to do is to construct a function f of mu such that f of mu is a lower bound for the minimum mean squared error gap for any mu. Now you may notice I dropped the squared on I. Of course, if we can construct a lower confidence bound for I, we can construct a lower confidence bound for I squared and vice versa. So I sort of will play fast and loose with whether I is squared or not. I'm going to call both of them the minimum mean squared error gap. Hopefully that doesn't cause confusion. So if we can construct a function f such that f of mu is less than or equal to I for any mu, and that f of mu somehow is easier to do estimation and inference for, and in particular that we can get a lower confidence bound for f of mu for any mu, then we're going to be in really good shape because L of mu is a lower confidence bound for f of mu, and f of mu is a deterministic lower bound for I, then L of mu is immediately a lower confidence bound for I. And we can proceed by data splitting to, there we go. So what we would do is we would split our data into two independent parts, use the first split to fit an estimate mu of mu star, and then we would plug that estimate mu into our procedure for generating a lower confidence bound L using the second split of the data. So we call this F a floodgate, and the reason we do is because floodgates, in the real world, are used to prevent flooding, and they should be able to deal with sort of any kinds of storm conditions. They should be able to handle worst case scenarios, and that's sort of the idea of this F, is that no matter what happens with mu, that's our sort of storm conditions, it's going to sort of hold your lower confidence bound below this critical level. So it's going to prevent your lower confidence bound from flooding above over this level I. And so I think floodgate is sort of an evocative name, and plus it allows me to use the symbol F for the function. That's nice. All right, so what exactly is F? I'm just going to write it down. So in order to define F, which has this exact form, I need to define x tilde. And x tilde is going to be in fact, it's a knockoff. If we're familiar with knockoffs, it's a knockoff of x, which means it's a conditionally independent and null copy of x, but whose conditional distribution is identical to x. So we take x tilde, and without looking at either x or y, we draw it from the conditional distribution of x given z. And so since x tilde is null, it sort of at least makes sense that in f of mu, which we hope is some sort of related to this measure of variable importance, that we see a difference between mu, which we hope sort of looks like mu star, so the regression function with the true x and z, and we subtract off the regression function with a null x and the regular z. So it sort of makes sense that somehow the difference between these two would tell us something about variable importance. Beyond that, the functional form is not at least super intuitive to me, but the most important property of it is that we can satisfy this first property of it lower bounding the minimum mean squared error gap. And indeed, we were able to prove that this is exactly true. So for any mu that you plug into F, it's going to be a lower bound for I. And importantly, in order to get tight confidence intervals, we actually have equality when mu equals mu star. So if you do a really good job and you pick mu equal to mu star, f of mu is actually going to be exactly equal to I. All right, so that's great. And in fact, this was the hard part. This is really the key idea behind our method and our idea. That's why this is what our method, which we call Floodgate as well, is centered around this Floodgate function. And coming up with f, I think really was the hard part, because what we're going to see next is that getting a lower confidence bound for f of mu, for a fixed mu, is actually not so hard. All right, so there is probably more than one way to do this, but we're going to take a model X approach where we assume that X given Z is known. I already mentioned this. We're going to quantify its robustness and then relax this assumption a little bit later, but for now, let's assume that X given Z is known. And remember that this is the definition of f of mu. And what you might notice is that, it's sort of a function of these two expectations. And now those two expectations, I no longer have this issue of unknown quantities inside nonlinear functions. My expectations are much easier to handle and get unbiased estimators for. So what I'm going to do is I'm going to take my data, which looks like yi, xi, and zi for I equals 1 to n, and I'm going to sample some x tildes. So x tilde I, I'm going to draw those for each I from the conditional distribution of xi given zi, and I'm going to draw each of them conditionally independent of xi and yi. So now I just have a sample version of x tilde, and I have sample versions of y, x, and z. And then I'm going to replace each of these expectations basically with its standard sample estimator. So simple as can be, the expectation that appears in the numerator, I'm going to replace with its sample estimator, and the expectation that appears in the denominator, I'm going to replace with its sample estimator. And in both cases, this is simple, mean of ID random variables. And so we have easy asymptotic normality results for both of them. And then f, of course, is a nonlinear function of these two expectations. And so we need the delta method in order to combine them, but we can do that. We use the delta method, we combine them, and so we can get a sort of an asymptotic normality result for estimating f of mu, which of course then means that we can use that central limit theorem to get a lower confidence bound, which we're going to call L sub n superscript alpha, where alpha is the level of the lower confidence bound, so that's coverage 1 minus alpha of mu. Now, you may notice that because I only sampled xi tilde once for each I, there's some randomness in this procedure, right? If I repeated this procedure, I would actually get a different result because I'd get different x tilde i's, even on the same data. But it turns out it's actually very, unlike some other Model X procedures, it's actually very easy to de-randomize this procedure. We just have to resample xi tilde a whole bunch of times, average things in the right way, and it all works fine. However, it turns out that all of our guarantees hold no matter how many times we resample x tilde I, which is sort of nice. So we don't need to resample xi tilde many, many times in order for our guarantees to hold. But if we do want to de-randomize our procedure, we should keep resampling xi tilde as much as we can. All right, so let's talk about what we can prove. So under these very mild conditions, so if mu is anything that has an eighth moment, and y has an eighth moment, and we have ID data, then our lower confidence bound covers. And we even quantify the rate at a 1 over root n rate, which is nice. And that really just comes from the central limit theorem. The fact that we had a delta method around our two central limit theorems made things a little more complicated. So that rate is not totally trivial, and we had to rely on some pretty recent Bayesian type results for the delta method. But we got it. It is a pointwise result, and so this is for a fixed mu and a fixed data generating distribution. And we certainly may be interested in questions about what happens when say z's dimension is increasing, or mu is changing. High dimensional questions as opposed to the low dimensional asymptotics that's sort of addressed here. And that's all going to sort of be captured in that constant in the big O term. And unfortunately, because of these recent results are very powerful, however, the constant that they produce is quite complicated, and it's not super interpretable. So we're going to take a slightly different approach to answering this question of what that constant looks like, or how our method might perform in high dimensions. So let's think about a certain class of mu. So if mu is partially linear, things get actually really nice. It turns out that the constant only depends on the scalar coefficient a in a partially linear model. Again, so we're constraining mu to be a partially linear model. or partially linear regression function, but it can be any partially linear regression function, and the constant is only going to depend on the sign of A. So, that simplifies things greatly. So for any fixed distribution, our convergence is uniform over any partially linear mu that you fit. And furthermore, it turns out that the constant only depends on the data generating distribution through, instead of the p plus 2-dimensional distribution of all the data, it actually only depends on it through the bivariate distribution of y and this sort of conditionally demeaned and standardized version of x. So this is even better than if it just depended on y and x, right? Because then maybe x's variance could grow or shrink, or its mean could change conditional on z. This is going to sort of get rid of all those things. So sort of ignore x's conditional mean given z, ignore its variance, and sort of distill it down to this one piece. Look at that thing's distribution with y. That's the only thing that constant is going to depend on. And so we can sort of imagine that as we move to high dimensions, as the dimension increases, as long as this bivariate distribution doesn't go crazy, so it has some bounded high order moments, then our convergence is going to continue to actually be quite good and only depend on a constant times 1 over root n. So this is a sort of a suggestive result. We'd like to understand this better, but it seems like it may be pretty flexible in the types of mu and high dimensional distributions that it can handle robustly. All right, now let's talk about an upper confidence bound. Well, unfortunately, I'm going to tell you that you can't get an upper confidence bound in the same way. And we have a surprisingly strong negative result to prove this. So suppose that there were no z, so no confounders at all. Then I squared would just be the variance of y given x, very simple. And trivially, I squared is upper bounded by the marginal variance of y. So it should be clear that an upper confidence bound that is greater than or equal to the variance of y really isn't telling you anything, right? It just says that x doesn't explain more variation than all of the variation in y. So of course that's true. And it turns out we can actually prove that under our assumptions, so we can bound some moments on y and stuff, but even after making some sort of basic moment assumptions, it's still impossible to even get a pointwise result that gives you a non-trivial upper confidence bound. So any asymptotically valid upper confidence bound that has coverage 1 minus alpha will asymptotically return a trivial result with probability 1 minus alpha, which basically says, this upper confidence bound is telling you nothing, because I don't even have to look at the data to produce an upper confidence bound that does this, really. Well, I'd have to look at y, of course, but I wouldn't even have to look at x in order to tell you this. So it's clearly not telling you anything about x's relationship with y. So, all right, what does that mean? Well, it means our confidence interval is sort of half gone, but I actually think it's not as bad as it might seem. I think a lower confidence bound already tells you a lot, especially in high-dimensional settings or the most exploratory settings. Usually the thing that we're worried about is how important is this variable that we found? Usually it's a secondary concern that I don't think anyone's too worried that it might be too important, right? We're worried that it's at least a certain amount of importance, and that's exactly what a lower confidence bound captures. And as we prove here, really to get an upper confidence bound, we would need to make some sort of structural assumptions on y given x, which comes with a whole host of challenges. In particular, sort of whatever structure we assume on y given x is immediately going to go into that upper confidence bound. And so we're going to be relying really hard on the types of assumptions we make there. All right, so we're going to focus on that lower confidence bound. And one of the first questions we might ask is, well, once we have it valid, can we say anything about its accuracy? How narrow is this lower confidence bound? And to talk about that, I need to point out that actually Floodgate is completely invariant to changing mu in certain ways. And in particular, if you replace mu with any member of this equivalence class, where you can take mu and add any function that's just a function of z, and you can multiply it by any positive constant, all of those mu's will return the exact same solution from Floodgate as if you plugged in the original mu. So this is sort of an equivalence class for each s mu. And so what I want to do is I want to link the accuracy of Floodgate to the accuracy of mu. But the problem is that mu is not really sort of well defined here, because there's a whole bunch of mu's that Floodgate treats identically. And so what we're going to do is we're going to pick a representative for this set. And so for any mu, I'm going to define the representative from its equivalence class as mu bar. So for any mu, every mu, sort of the bar over it denotes that I'm taking the representative from the equivalence class S mu, such that mu bar has the same conditional expectation as mu star, and mu bar has the same expected conditional variance as mu star. So it turns out this uniquely defines, and it always uniquely defines exactly one representative from S mu for any mu. And you can sort of see that since we're matching mu star, we're trying to pick a pretty good representative, right? So we generally expect that mu star is going to be better than mu as an estimate of mu star. And so this is actually going to help us because our theorem says that, under some mild regularity conditions, the half width, so I call I minus the lower confidence bound the half width, because if we were a confidence interval, that would be a full width, but we're sort of only capturing half of that since we only have a lower confidence bound. So this half width can be upper bounded exactly by a function of the mean squared error of mu bar n, plus a parametric rate that we're never going to beat, right? We're never going to get lower than 1 over root n because we're using a central limit theorem, and so the width of our central limit theorem results around f of mu is never going to be narrower than 1 over root n. And the first term in this big O expression captures the gap between f of mu and I. And so by directly relating that to the mean squared error of mu, or actually the mean squared error of mu bar, which we generally expect to be even lower, this gives us what I think we hopefully expected from the beginning, which is that the accuracy of Floodgate is directly related to the accuracy that we're able to estimate mu star. So that's kind of nice because it says if we know a lot about our problem, we're going to get a narrow confidence interval. If we don't know a lot about our problem in terms of y given x and z, we're still going to get a valid lower confidence bound, but it's not going to be as narrow. And I think that's sort of as much as you can hope for to efficiently integrate information to getting accurate inference while gracefully degrading when you have less and less information. Next, we're going to talk about robustness. I promised you that I'd talk more about this model X assumption. And so suppose that instead of knowing the conditional distribution of x given z, which I'm going to denote as p x given z, that we instead only have an estimate of p hat of x given z. Well, we can prove that the validity or the coverage of our lower confidence bound still looks like the same validity we had before, the 1 minus alpha minus O of 1 over root n, with another term. And that term has two parts. It has a delta, which I'll tell you about in a sec, and then it has a total variation distance between the p x given z and p hat x given z. Now notice that the x and the z's in there are actually vectors. So that's the total variation distance between the n-dimensional conditional distributions of x given z for p and p hat respectively. Okay, so that makes sense, right? It's nice that we can quantify the error of our procedure in terms of some sort of distance between those measures, but perhaps not too surprising. What I think is maybe more interesting and surprising is this delta term. And note that there's a min around the delta and the total variation distance, which means that delta can only help us, right? Because we're taking a min between these and it's being subtracted. So if delta is smaller than the total variation distance, it's going to save us, even if we have a bad total variation distance. And delta, it turns out, is actually an indicator function, which is rendering really weird in these slides for some reason. I didn't think it did that on my computer, but anyway, that weird Tetris-looking thing is a 1, and so this is an indicator function of the set that's in curly braces, and the set in curly braces. So this delta either takes the value 0 or 1. Of course, if it takes the value 1, it's useless, and it doesn't help. But if it takes the value 0, then it actually doesn't matter how badly we estimated px given z. And it takes the value 0 when, and so we have this inequality inside the indicator function that on the left-hand side has a constant times a measure of the quality of our estimation error, or a measure of the estimation error in estimating x given z. And on the right-hand side, we have, again, this mean squared error of mu bar n, and divided by I. So there's sort of two takeaways here. which is that, okay, Floodgate is robust if we can estimate the conditional distribution of x given z well enough. That makes sense. We quantified it. That's good. But furthermore, if we actually have an important variable, so the variables we sort of care the most about are the ones that have positive minimum mean squared error cap. In that case, it turns out that Floodgate is also robust if we can do a better job of estimating x given z than we can of estimating y given x and z. And so this sort of says, if you have more information about the covariates than you have about the outcome given the covariates, you might actually expect that the delta might be able to save you, at least for the positive variables, which I think is kind of nice because, again, if you have some unlabeled data or domain knowledge about the covariates, you might actually expect that you know more about x given z than you know about y given z. All right, and then the second thing about robustness is that we can actually relax the assumption sort of more directly and say, okay, what if I actually don't want to assume that I know x given z or even estimate it. I just want to assume that I have a model for x given z. Well, what did we use x given z for in the Floodgate procedure? Well, there's only one place that we used it, which was drawing the x tildes. And so what are we going to do instead? Well, when we have a parametric model, we can often find a sufficient statistic, t, that we can condition on additionally so that p, x given z, and t is actually parameter free, right? By definition of a sufficient statistic, if you condition on a sufficient statistic, the distribution no longer depends on the unknown parameters. And so we, at least in principle, can now sample x tilde in Floodgate from this extra conditional distribution, even though we don't know the parameters in the model because we've conditioned on a sufficient statistic. Okay, so we were at least able to replace that step in the procedure, but because we're now conditioning on t of x and z, and notice those are both x and both z again, so that's all of the data, we no longer have independence between our x tildes. And so we no longer have IID samples, which is going to hurt our central limit theorem. The way we fix that is that we're actually going to split our n samples into a whole bunch of batches. And each of those batches is going to be independent, and within each batch, we're going to draw x tilde conditional on the sufficient statistic for just that batch of data. And so we're still going to have independence between batches. We're going to have some dependence within batches, but we can actually take care of that. So it turns out that by doing this, so again, batching your data, within each batch, conditioning on a sufficient statistic and drawing x tilde conditional on a sufficient statistic for that batch, and then stringing all of the x tildes together and then plugging them into Floodgate as usual. No other changes are necessary. If the number of batches goes to infinity, so we just need to, not have a fixed number of batches as n goes to infinity, then conditional Floodgate, so that's the conditional version of Floodgate that I just described, remains asymptotically valid. So the same theorem for validity holds. So the only thing we might suffer from, which we might expect since we're weakening our assumptions, is that we may lose accuracy. But it turns out that as long as the number of samples per batch also goes to infinity and does so at a faster rate than the number of batches, then we actually get, at least up to a constant, the same accuracy bound as for regular Floodgate. So that's pretty nice. We show how to do this, how you condition and how you sample. What sufficient statistic to use is going to depend on the model, and it's definitely not always going to be possible. We show how to do this for x given z being Gaussian or a discrete Markov chain, and I think the high-level message here is that we can, in some cases, relax the Model X assumptions by conditioning on a sufficient statistic, and we actually don't really have to lose much in the way of accuracy. At least the rate stays the same. All right, I'm going to have a couple simulations to show you. The first is on accuracy. So this is a simulation in 1100 dimensions, and it has a highly nonlinear model for y given x and z. We're going to run Floodgate on 3 different algorithms for estimating mu, and we're going to estimate mu by estimating mu star with mu by sample splitting, and we're always just going to do 50-50 sample split. We actually found that was a pretty good choice across a lot of settings, was to do roughly 50-50 split. And so you can see the sample size denoted on the x-axis. So whatever the sample size, we're always going to use half for estimating mu star and picking mu, and the other half for Floodgate. And what we see is because this is a highly nonlinear model for y given x and z, and because of the symmetries, the invariance of Floodgate, the two linear methods, lasso and ridge, do almost exactly the same thing. They have the same path width and the same coverage. Notice that everyone's coverage is actually above 95%. This shouldn't be too surprising because, again, our Floodgate procedure gives sort of 1 minus alpha coverage for f of mu, but f of mu can be bounded away from I. And especially in this highly nonlinear model, we don't expect that our estimated regression functions are going to capture all of those nonlinearities, so we expect that bound to be non-zero. But we do see that we gain something significant by moving to a nonlinear procedure. So SAM is sparse additive model, and we see that gives us actually a substantial reduction in the half width, and that's because it's able to do a better job of capturing the nonlinearities in y given x and z. And we can see that as the sample size increases, our confidence interval width goes down. All good. On the robustness side, I want to show you what happens if you do something that we didn't really cover in our theory, but that would be very natural to do in practice, which is just to estimate your x distribution from the actual data you have. And so that's what I'm showing here. Now I actually have 4 algorithms that I try, and I'm comparing for each one the dashed and the solid line. The solid line says run Floodgate using the true x given z distribution. What the dashed line says is take some subset of your sample, and that's what's on the x-axis, is sort of how much of my sample size do I use to try to estimate x's distribution. And in this case, x is multivariate Gaussian. It sort of follows an AR1 model, and we're going to estimate its covariance matrix using the graphical lasso. Sort of, a reasonable thing to do, but in a high-dimensional setting, it's, in an absolute sense, still not going to be a very good estimator of the distribution. And yet we see pretty impressive, I think, robustness in that there's very little change, even when we use as few as 100 samples. So remember, this is an 1100 dimensional distribution to estimate that covariance matrix with as few as 100 samples. Again, that estimator is going to be quite bad. However, Floodgate's inference is quite robust. The half width barely changes. The coverage dips down a little bit, but we're talking a couple of percent, and so it's really not a problem. All right, and I'm going to end just to conclude. Floodgate is a new inference method for variable importance. It has a number of desirable properties, which is that it provides inference for this minimum mean squared error gap, which I think is a really interpretable yet sensitive non-parametric functional that measures variable importance. It seamlessly leverages any kind of regression estimator that you might want. So it can use machine learning, it can use domain knowledge, however you want to estimate mu star with some mu. Floodgate can take advantage of that. And in doing so, it assumes essentially nothing about the conditional distribution of y given the covariance. And instead, it assumes knowledge of x's distribution, but we quantify the robustness, and we can actually show that we can relax that assumption a little bit sometimes. And so, we think that's not too bad. We think the results are pretty strong, and this is worth thinking about. That's it. Thank you very much. Look forward to talking to you all in the discussion.